All right, so you'll see that the graphing calculator already has an inverse for matrix set up, and that's from the previous video. So make sure you watch that to see how we came up with that inverse. Well, there's this really neat thing that we can do where we take something like this system of equations and we rewrite all of this in terms of matrices. Okay. Now we've kind of done that before where we, would do an augmented matrix, do reduced row echelon form, and we can see the solutions. But there's something else that we can do here. So if we see this as matrix A times X is equal to B, and what we'd really be saying is if we take the matrix here of 1, 2, 1, 0, negative 1, 3, 2, 1, negative 4, and we'll say times X. So X is going to be representing your solution. So in this case, X, Y, Z. And you might say, what? Well, think about this. If I were to take this row right here, and I were to do the matrix multiplication, then you would kind of turn it on its side and do 1 times 1, 2, and 1, and you'd multiply that. And so that still gives you 1x, 2y, and 1z, right? Same thing if you were to use the row 0, negative 1, 3. All of this then is equal to what would be your constant matrix of negative 3, negative 7, and 3. Okay, so just kind of keep that in mind. We're kind of rewriting it this way. But the way we solve this is by using inverses. Now, you might think, oh, can't I just divide both sides by A? It doesn't work that way because it's not a linear equation. What we can do, though, is that we can apply the inverse on both sides. So if I apply the inverse here, I would also have to apply the inverse here. Now, order does matter, and the placement does matter. So I have to apply the inverse on the left side of each side of the equation. So when I do the inverse times A, I'm just left with X representing my variables X, Y, Z. And on the other side, I have A inverse times B. Okay, so that means that my solutions given by X, Y, and Z to this system will be equal to taking the inverse of that 3 by 3. That, again, we found this in a previous video. We still see it here on the calculator. So that's 1/15, 3 over 5, 7 over 15. Then we had 2 over 5, negative 2 over 5, negative 1 over 5, 2/15, 1/5, minus 1/15. So if I take that and then I multiply that times those constant values, on the right side here, this is just an exercise in multiplying matrices together. When I do that, that will tell me what the solution is to my system. So let's check that out. Let's actually do that. So starting with this row right here, give myself plenty of room. So I'm going to take this and do it like this. So the 1/15, 3 over 5, 7 over 15. Okay. So this gives me, let's see, negative 3 over 15 is negative 1/5, then minus 21 over 5. And then that's going to be plus, the 3 is reduced, that's going to be 7 over 5. All right, then I'm going to do the same thing with my next row, right? So if I use this and I turn that vertically and I do the product, so that gives me negative 6 over 5 plus 14 over 5 minus 3 over 5. And then do this one last time with that last row. So flip that guy, 2 over 15, 1/5 negative 1 over 15. So that gives me negative 2 over 5, negative 7 over 5, and then negative 1/5 when you simplify that. All right, so now let's put all this together. We've got negative 1, negative 21 is negative 22, plus 7 is negative 15 over 5. So that's just negative 3. So negative 6 plus 14 is 8, minus 3 is 5 over 5, so we get 1. And then here, negative 2, negative 7, negative 1 is negative 10 over 5, and we get negative 2. So we're saying here that our solution to this system is the ordered triplet negative 3, 1, negative 2. Again, you can easily check that. But you know what? We've got a calculator. So let's double, triple check everything. So let's change this into a 3 by 4 matrix. Now, cool thing here is that when I did that, it still has the same coefficients that we have here on the left side. The 1, 2, 1, the 0, negative 1, 3. We just have to get over here to the constant. So we said this is negative 3, negative 7, and 3. And now we can go and do our matrix math, reduced row echelon form of matrix A, and we have negative 3, 1, negative 2. So we could have done all this by, well, so many different things that we could do. We could have used Cramer's rule. We could have used elimination or substitution. We could have done reduced row echelon form as an augmented matrix. Or what we did here, we found the inverse of the 3 by 3 formed from the coefficients of the 3 XYZ equations, and then we multiply that times the constants, and we get our solution. So a lot of cool options that we have here. And a lot of these are just, they're algebraic. You use an algorithm, there's a process for it, so there's no guessing and checking. Yes, you may have to deal with fractions, but it's a method, and it works. Well, provided that you don't end up with a determinant of 0, or that you don't have something that is, say, no solution, or like an infinite number of solutions, because then finding the inverse doesn't quite work out the same way. But anywho, a lot of neat things you can do with matrices.